About to go into the stock room. Got to get the starch ready for the vitamin C lab. So let's go find it. Let's see here. I think it's over here. M's. S's. That sounds like starch should be around here. Sucrose. I don't need sucrose. Ah, here's some starch. And different kinds of starch here. I think I've been using this starch potato. Let's try the starch soluble. Don't know where this comes from, either potatoes or corn or something. I think I'll try that one. No, I better go with potato. I think that's the one I've used before. It's good not to change if you don't have to. Okay, now I gotta find the bottles to put that starch in after I make it. So I'm gonna check down here. Nothing. I think it's in the other lab. Let's go look. I think it's in this lab. Here it is. These are some bottles that I've used in the past. Has everything I need as far as the bottles go. But the starch bottles are missing. Dang it. Okay, well, I found the starch bottles. They're right here. Sitting here, out in the open. The bad thing about that is starch doesn't stay good for very long. There's some type of fungus or something that likes to grow inside of starch solutions very easily. The label on it said it was made on the 2nd of last month, so it's a little over a month old. I'm going to look in here and see if I see any evidence of that fungus in there. If it's got like a cloudy, milky white substance, then it's probably not going to work. You see anything in there? It looks pretty clear to me. I guess I should pour it into a white container, or I mean a glass container to look at it more carefully, but I'm going to say it's probably good. That'll save me a lot of time having to mix up a new starch solution. And I got another bottle of it right here. And I think this one was made at the same time, even though it doesn't have a date on it, which isn't good. I should always have a date on there, but it was probably made at the same time. Alright, so I found 3 bottles of starch solution altogether. We don't need very much of it, but I got the starch, and these dark colored bottles are the iodine bottles that I would use if I had a whole class of them. And they got solution in them, but it's from last trimester, so several months old. So also need some vinegar or 5% acetic acid solution. Got that, so let's go see about setting this lab up then. Alright, so a really easy way to check that starch solution. So the easiest thing to do is just put in some water in a beaker. Put a little dollop of the starch. Stir it, stir it, stir it. You can even add a little taste of the vinegar if you wanted to, but we don't really need that for this little check. Okay, you ready? Let's see if it works here. If it's good starch, guess what will happen when I put in the iodine? Bing! Looks like it'll work. So next I got to decide whether or not I want to use this iodine, this old iodine solutions that have been in here since last trimester. These all have something in them. That one's full, so that's a lot of iodine just to dump down the drain and not use, for one thing. For another thing is you know, it saves me a lot of work if I don't have to mix up a new solution of iodine every trimester. And so, again, we're not looking for ultra high precision for this introductory lab, just something that is demonstratively useful and reasonably accurate. Well, I got to go to the other lab to get the apple juice here, so coming through the stock room into the organic lab. It's the mirror image of the inorganic lab. Woohoo! To the refrigerator where I have the apple juice. And this is our old yucky refrigerator. I won't show you how yucky it is. It's rather embarrassing. But here is a new, nice, cold bottle of juice. Generic brand, great value. From concentrate with added ingredient. Guess what that added ingredient is? Ascorbic acid, which is commonly called vitamin C. That's what we're trying to measure, is how much of ascorbic acid is in this bottle of juice. It says 130% vitamin C daily value per serving. That's a lot of friggin' ascorbic acid in this one little bottle. Alright, so let's check the iodine solution that we might use. Down the drain with the starch check. Don't need that for anything at the moment. Okay. All I need to do for the check is, well, easy way to do it. I'm going to kind of sort of do it like the actual experiment will be set up. That's basically what I'm going to do. So I need about 20 milliliters of the juice. 20 milliliters of the juice right about there. I don't know if you guys can see that now. Let's put it here. Yeah. 20 milliliters. It doesn't have to be exact. This is just a little check. Okay, so there's 20. Actually, it's probably a little less. So I'm going to put a tiny bit more. Ooh, that's probably too much. Oh well, this is just a check. So I got the juice, and now in the regular procedure, regular lab procedure, you guys are going to add some vinegar to the juice. This is supposed to preserve the vitamin C that's in there, the ascorbic acid that's in there, so that it doesn't react or break down, degrade while you're trying to measure it. So you don't want it to degrade before you measure it. You want it to be in top form and every bit of it to be present. Now, I got a total of a little less than 50 milliliters. Now for this check, it's going to be semi-quantitative. I got a graduated cylinder here, 25 milliliter graduated cylinder here. I think I'm going to use this bottle of iodine. Since this one is full, this is about 200 milliliters of iodine right here. I'm just going to take and see if it's good. So if it's good, then it'll take a lot of this iodine to react with all the ascorbic acid that's in the juice. And I'm going to explain that in more detail whenever we get in the classroom on the board. But I'm going to first start with 10 milliliters of the iodine. Oops, you know what I forgot? Starch. Got to have the starch in there. So a little dollop of starch. There we go. Stir that up. That's my juice mixture for the quick check. This is under 10 milliliters. Now, what do you think it's going to have? Remember when it was just water and starch and I put in the iodine, remember? It turned color. Purple. Nice purple color. Well, let's see what happens here. Maybe you need to see close. Here you go. Alright. Pour it in there. Purple, purple, purple. What the? Hey! The purple color was there, but then it was gone. Did you see that? That was pretty crazy. Let's try that again. 5 more milliliters of iodine. Whoop, that's 6 more milliliters, 7 more milliliters. Let's try that again. Ready? Man, what happened to that color? It just disappeared. That's amazing. Let's try 5 more milliliters. There's 5 more milliliters, and I know this is just going to disappear because the first 5 milliliters disappeared almost instantly. So watch this. It's gone. It disappears like nothing. So that's 20 total milliliters. And because it disappeared so fast, guess what? I'm going to go ahead and go up to 10 more milliliters. Now I know this is a lot. Let's give it a shot. That'll be a total of 30 milliliters roughly. Down the hatch. Oh, that color is dark. Think it's going to disappear? No, it didn't. So you know what that tells me? That the end point, which I'll explain more in the classroom in just a minute, and we will have another lab towards the end of the term that talks a lot more about endpoints as well when we do an acid-base titration. But this simple check told me that the endpoint for the iodine oxidation of the ascorbic acid is between 20 and 30 milliliters, which is a-okay, pretty ideal amount for doing your typical titrations with. So I'm going to go ahead and use the iodine solution and starch solutions that I already had pre-mixed, and that'll save me a nice chunk of time. Glad that we checked this. Now I got to get a few other things together for the rest of the experiment. Burette, flasks, and magnetic stir bar. I think the burettes are in here somewhere. Here they are. Ah, dropped one on the floor. Don't want to break it. That looks like a pretty good one. And here are the flasks. For this lab, I like to use 125 milliliter flasks. Let's see if I can find some nice clean ones. Yeah, I don't know if those are clean. Ooh, that one looks pretty dirty in the middle. Maybe I'll get a different one. That'll give me at least 2 that look pretty clean. Alright. And need a burette stand. Alright. There's a nice burette stand. But that looks stable enough. I need my flasks. Where are the stir bars? I need the magnetic stir bars. Well, here's an inconspicuous place for magnetic stir bars in the stock room. Now watch and be amazed at the power of the stir bar. Oh, that's a big one. I don't need one that big. You know, it's the simple things that can really impress people sometimes. Ooh. Okay, so we're back at the board now. So I trust you all can find, well, this lab sheets, and notice on this one the introduction is much shorter. It's a different format. So don't forget to do the 3 pre-lab study quiz questions. They're super easy. Of course, you should read the intro to help to get the answers for those. Now I'm going to go over just a few things about the background theory. Vitamin C is most commonly thought of as ascorbic acid. What we got for our reaction, a very simplified version of it, I'm just going to write it like this, of AA is ascorbic acid. Okay, and of course in your lab procedure, they give you a molecular structure of ascorbic acid and compare it to glucose. Well, we're not going to go into all of that much detail right now. But you see that all that we really need to know for this lab is that 1 mole of ascorbic acid reacts with 1 mole of iodine. Iodine is our oxidizing agent. An oxidizing agent is something that oxidizes another substance, of course. And what does that mean? Well, when you hear the word oxidation or oxidize, an element usually pops in your mind. What would that be, maybe? Oxygen. Yeah, oxygen is where we get the term oxidation, of course, because oxygen is a great oxidizing agent, but it's by no means the only oxidizing agent. Most nonmetals can be oxidizing agents, okay? And iodine is what we're using here as a very strong oxidizing agent. And it will oxidize the ascorbic acid. Now, if you read up on nutrition and things, they'll say, you'll come across the idea that ascorbic acid or vitamin C is a great antioxidant. So if you have ascorbic acid in there, then guess what? It can knock out the iodine. And so it's an antioxidant when it does that. Of course, that's just a single example. There's many, many other types of substances that are potentially harmful oxidizing agents that can get in or do get into your body, and things like ascorbic acid needs to knock them out before they do damage to your cells and tissues and on up the chain. So ascorbic acid reacts with iodine. It gets oxidized by iodine, and it forms what is called dehydroascorbic acid. So I'm just going to put dehydro AA. Okay, that's dehydroascorbic acid. And on the more fundamental level, when something is oxidized, it loses electrons. Okay, so the ascorbic acid gave up electrons. Now, where do those electrons go? Well, they go to the iodine. And that is the basic definition, or the fundamental chemical definition of oxidation, is it takes electrons from something. So iodine is taking electrons from the ascorbic acid, and that converts the iodine into iodide. Okay, this is a very simplified version of this reaction. It's not terribly complicated, but we just need the basics on here. And that's practically all we need for our interest. Mainly the idea, again, that 1 mole of iodine reacts with 1 mole of ascorbic acid. That's the main thing that you need for many titrations, is just how many moles of this react with how many moles of that, and then you can figure out the math that is relevant to what you measure in the lab. All right, how much iodine is required to knock out all of the ascorbic acid? And of course we want to measure it in the juice samples. So all we need to know is the concentration of the iodine that we're working with, the amount of juice that we start with, and the fact that 1 mole of iodine reacts with 1 mole of ascorbic acid. The math for this lab is much less involved than the previous 2 labs, so that's good news for those of you who might not like all that math. You just have a very easy calculation compared to those other ones. It's just 1 step is the way it's broken down. But I'm going to show you a little bit of background where that 1-step calculation comes from real quickly here. So if we want to know how many milligrams of ascorbic acid are there, well, the formula down here on the bottom says this right here. Milligrams of ascorbic acid is going to be equal to the milliliters of iodine used, that's in the titration that we're going to set up with the burette and the volumetric flask and this stir bar and everything. How many milliliters of iodine was used to reach the end point? And so that's a key idea, is the end point. Remember, the solution turns purple after you added enough iodine to the juice. And when it turned purple, you are past the end point. Okay? But when the iodine reacts with that ascorbic acid that's in the juice, it gets pulled away from the starch, and so the color disappears. Okay? So you added a little bit of iodine, and it hit all the ascorbic acid, it reacted, and it disappeared. The purple color disappeared, and it was all converted to iodide. The iodide over here doesn't react with the starch. Okay, so that's why it's colorless and clear after it reacts with all the ascorbic acid. Then you add a little bit more iodine, and it disappears again. Then you add a little bit more, and it keeps on disappearing until when? Well, it keeps on disappearing until you finally have 1 drop extra iodine, no more ascorbic acid, and instead the iodine hits the starch. I'm going to put it down here like this. Starch turns into a purple complex. All right? And that's if the ascorbic acid is all gone, then the iodine will hit the starch and it won't get pulled away from the starch anymore. It will just turn into that purple color with this, making a complex, this complex molecular structure of iodine and starch, and it turns that purple color. And then we know that we've consumed all the ascorbic acid. All the ascorbic acid is gone because the purple color didn't disappear anymore. That's the end point. All right, that's the end point. So how many milliliters did it take? That's what we use in this formula here, the milliliters of iodine used to reach the end point. And so it's gotten it broken down to a very simple multiplication. You say times 0.53, that's milligrams of ascorbic acid per milliliter of iodine. Okay, so we say how many milliliters did we use? Maybe that was, let's just make up a number and say, what if it was 15? Okay, so I'll put it like this. Let's say it was 15 milliliters of iodine that we used to reach the end point. For the sample or the setup, we saw that it's going to be between 20 and 30 milliliters of iodine, right? Well, let's just say it came out to be 15, lower than that, just for example. Well, all we need to do is take that and multiply it times 0.53 milligrams of ascorbic acid per milliliter of iodine. And you see that milliliters of iodine cancel, and that leaves you with just your answer, milligrams of ascorbic acid, which, if you can see, 0.53 is about half, so it's going to be a little over 7.5. Let's say 7.7 milligrams of ascorbic acid. And you say, well, that was in the juice sample. And I need to get a calculator to double check that. I'll go grab one in a second. But anyway. Oops. Anyways, the point is, that many milligrams of ascorbic acid was in your juice sample. Okay? And in the setup, you saw I poured about 20 milliliters of juice into the beaker. And that's what you're going to start with. That's what we're going to start with in the flask in a minute, is I think 20 milliliters of juice. It says right here, in the procedure, it says 20 milliliters of juice for each flask. Now, the question that I wanted to get to real quickly is, where did this 0.53 come from? Okay, because it's all fine and dandy to have a magic number to get out answer to a question, but as scientists, we want to know where those numbers come from. And so we start with the concentration of the iodine. That's the key that you need. So on the procedure here and in the lab, we are going to use the concentration of the iodine. It's 0.003 moles, so per liter. So iodine, whenever you have concentrations in chemistry, and this is coming up much later in the text as well in the regular class assignments, we have square brackets around a substance or around a formula. Square brackets around a formula means the concentration of that substance. And generally it's going to mean what we call molarity. Okay, molarity is, for the iodine, is 0.003 moles per liter. Okay, that's what molarity is. It's how many moles of the substance per liter of the solution. And so that's the concentration of the iodine. Well, that gives us valuable information that if we know the volume required to reach the endpoint, we just multiply it times the concentration, and that tells us how many moles of iodine was used. So that's what we set up here. We used 15 milliliters of iodine to reach the endpoint? Well, let me go ahead and convert that concentration, or say, since we got 15 milliliters here, and the formula on the procedure here is written in terms of milligrams and milliliters, I'm going to go ahead and convert this, say, to milliliters, so it's moles per milliliter. Well, of course, if you want to get rid of liters, then you can say 1 liter up top per 1,000 milliliters on the bottom. And you see that will cancel out liters and leave you with milliliters. So that would be 0.003 divided by 1,000 would put you in terms of moles per milliliter. Okay, and we don't have to punch that in our calculator and write it out yet. But that will take care of the units for us. So now we're in terms of milliliters of iodine. Now this is of an iodine solution. Okay. Now, from the Balanced reaction, this is the key. This is called the mole-to-mole conversion. We know 1 mole of iodine reacts with 1 mole of ascorbic acid. So I'm going to go ahead and put in here, this is moles of iodine right there, right? That's what we're talking about for this concentration. And say, well, we want to know how many moles of ascorbic acid will that react with? Well, from the balanced equation, we know 1 mole of ascorbic acid reacts per mole of iodine. Right? And again, this is just background information to see where this 0.53 comes from. And now this is the bread and butter of chemistry. It's mole-to-mole conversions, dealing with concentrations, and all of that type of thing. So I'm hoping this is valuable to you to understand a lot of this material that will be coming up and that you're dealing with currently. We got mole-to-mole conversion right here, and it will leave us, well, you see moles of iodine cancels. Whatever's in the numerator, it will cancel if you have the same thing in the denominator. And so that leaves us with moles of ascorbic acid per milliliter of the solution, per milliliter of the iodine solution. Well, great, but we don't want moles. Most of the time we want grams or milligrams or something like that. So we can take, though, and convert the moles of ascorbic acid to grams using the molecular weight of ascorbic acid. And that's where you get this 0.53 from, is when you multiply it by the molecular weight, because if you take, say, 176 grams of ascorbic acid per mole of ascorbic acid, that is the molecular weight of ascorbic acid. You can look that up and see for yourself. And so that will cancel out moles of ascorbic acid and leave us with grams of ascorbic acid. Now, if you look on here in the procedure, of course, you'll see that it's in terms of milligrams of ascorbic acid. So we need one more conversion factor, of course. That would be, excuse me, that would be 1,000 milligrams per 1 gram to convert to the milligrams. And that, of course, cancels out grams and leaves us with milligrams of ascorbic acid per milliliter of solution. That's all that we are left with. And notice that we divided by 1,000 here, we multiply by 1,000 there, so the thousands cancel out. And all that we're left with is 0.003 times 176. Guess what that comes out to be? That comes out to equal 0.53 milligrams of ascorbic acid per milliliter of iodine solution. Okay? So that's where this number comes from right there. That's our conversion factor between milliliters of iodine that we use in the titration and milligrams of ascorbic acid that we're going to say is in the solution after we multiply it like this. And remember, when we multiplied it, 15 milliliters times 0.53, we say, well, if that was your result, then you would say, oh, it's 7.7 milligrams of ascorbic acid in that juice sample. go! Alright, so let's go ahead and go to lab, and we'll come back to this idea in a minute after we do the lab, okay? It's time to put on the goggles, go into lab. Gotta love goggles. Somebody turned on the lights in the hallway for some reason. It's a lonely building these days. Right. In the lab we are. Okay, so the first thing you got to do to set up your titration, or before you do the titration, is make sure your burette is in working order. This is the stopper, and when you turn it perpendicular with the rest of the burette here, that's when it's closed, and when you open it up parallel with the rest of the burette, that's when it's open, and it will drain out the tip. So I'm going to make sure that it's not leaking, the burette's not leaking anywhere around the stopper, and of course that it drains smoothly from the tip. So I'm just going to fill it up with water, and that will also help to rinse it. So I'm just turning on the water here and filling her up. And there we go. And do you see any leaks? I don't see any leaks. It's looking like it's holding. Now let's open it up and see if it drains. Yes, I got a beaker down there to catch it. It looks like it's draining very smoothly. That's good. That's what we want. Of course. Now I'm going to go ahead and dump out most of the water. I like to check to make sure that it drains when it's full. When you dump out most of the liquid, though, the pressure is much less, and sometimes the stopper might not drain smoothly when it's down low on liquid. So I like to find that out and test that it's still draining smoothly when it's on low liquid level. And it looks like it's still draining just fine on low liquid level. So that counts as the first rinse for the burette. So I'm going to dump out the rest of that water. That was the aqueous rinse. And if you know the burette's not very dirty, then you don't have to do a lot of rinsing. The next thing to do is get the solution that you're going to fill the burette with and rinse it with that solution. So here's the iodine that we tested out earlier, and I'm just going to fill the burette up a small amount just to rinse the inside of the burette with this iodine solution. So here we go. Just want a few milliliters in there. That's plenty. Now this is what I like to do as well, and this is, different people do this different ways, but I don't like to fill the burette all the way up. Now see, around the edges, or I'm sorry, the sides, the inner walls of the burette, there can be contaminants, and so to get rid of those contaminants, water droplets could be one of those contaminants, and that could dilute your solution when you pour it in the burette. So we don't want that, and so to get rid of that, you can rinse the inside of the burette with the solution that you're going to use. So I like to go ahead and turn it horizontal and hold that over the sink. Without draining it, though, I can watch the liquid go down and turn it in my fingers here to rinse out any water droplets and contaminants on the inner walls of the burette and not spill it at the same time. So that seems like a pretty good rinse. And I'm just going to turn the water on here and drain the iodine down the sink. Now, iodine is a very strong oxidizing agent. It's a common antiseptic that is used in hospitals to sterilize instruments like surgical tools, and sometimes I've even heard that doctors would, rinse their hands in iodine solutions. Anyways, the reason it's good for that type of thing is because it oxidizes the mess out of everything. And so if you get it on your skin and it's very concentrated, it will sting very badly. If it's dilute, like we're using a very dilute solution, then it might have to sit there for a while, and it will, at minimum, it will stain your skin. But if it got into a slight scratch or something, then it would start to burn very badly, similar to how alcohol burns if you put that on a scratch. Anyway, so I drain that down the drain, and it gives off an odor similar to chlorine. If you go to a pool, public swimming pool, you smell the chlorine in the air. That's similar to how iodine is a little bit more pungent maybe than chlorine. And you don't want that odor building up in the lab. So I like to rinse it down the drain with running water right away. Now all I'm going to do next is fill it up. A lot of times I like to have funnels to fill up burettes with. So here's a funnel. I can make it a little bit more convenient. If you're careful though, you don't have to have a funnel. So I'm going to go ahead and use the funnel though, so I don't have to be quite as careful. You just got to be careful though to still go slowly so you don't overflow the burette when you're filling it up. So I'm filling it up, and I like to fill it past the 0 mark. Whoa, that's very full. Okay. And then I will open up the stopper very quickly to knock out any bubbles in the tip and drain them down, and also to rinse the tip out. And I will drain it down to start exactly on the 0 mark on the burette. Okay, so the tip is nice and filled, no bubbles in the tip of the burette to throw off the volume measurements. And now I'm just going to drain it so that the bottom of the meniscus starts exactly on 0 on the burette. That's a convenient starting point, 0, right? Let's see here. Bing. Okay, there you go. Take a look at it. Dang it. Focus. Focus. Alright, now we put the burette in place right above the flask, and it's ready. Next I'm going to prepare the juice solution, and that's pretty easy to do. All that we need is 20 milliliters of juice. That's what the directions say. 20 milliliters of juice. Okay. Looks like I'll be using this one. All right, 20 milliliters of juice. Remember, the vinegar though is intended to preserve the ascorbic acid, so I'm going to go ahead and put the vinegar in here first to help to knock out any contaminants that are in there to preserve the ascorbic acid in the juice. So it says 25 milliliters of ascorbic acid. I'm sorry, a 5%, 25 milliliters of a 5% acetic acid solution. Vinegar is acetic acid. It's 5% when you buy distilled white vinegar from the grocery store or whatever. So 25 milliliters of that. Now, you don't have to be super precise on the vinegar because we're not trying to measure the vinegar. We're trying to measure ascorbic acid through this whole procedure. So that should be good enough on the vinegar. Some in there, 25 milliliters. Now, we're going to do this at least twice and see if we get good results from 2 trials. And now we need to measure the juice, 20 milliliters of juice into each flask. Now I'm going to try to be a little bit more precise on this one. Maybe I should even break out a plastic pipette. All right. So 20 milliliters of juice. Try not to be overwhelmed with all the excitement. I might just put this in fast motion for you. That would be nice of me, huh? Next up, let's do the starch. 1% starch. And it says 3 milliliters of starch. Now, you definitely don't need to know the starch precisely with its volume. So all you need is a consistent amount and enough to see the purple color, which doesn't take much at all to see the purple color because it's a very, very dark purple color. That's why it's a good indicator. The starch is a good indicator for the iodine. So I'm going to just add 1 squirt, and I'm going to make the squirts the same in each of these. Ready? 1 squirt. 1 squirt. And I don't even know if y'all can see this, can you? Can y'all see this? Raise your hand if you can see this. Okay, I put 1 squirt in each of those. Now I need to put 1 squirt in this one. 1 squirt. All right. All right, got that. Okay, there's my 3 starting solutions. Let's take a closer look. Do they all look the same to you? They all look the same to me. Now, on to the titration. So, we're trying to add the iodine up until it turns purple and stays purple for at least 30 seconds to a minute. But I've got to get a better stirring plate than this thing that's all catty corner. So hang on 1 second. There we go. Isn't that a better fit? Okay, so I'm going to put you all down close here to see the action. Turn on the stirrer. Oh yeah, auto stirring. And commence the titration. I'm going to add the iodine. Now at first I can add it quickly because I know that it's not going to change until somewhere after 20 milliliters of iodine has been added, according to our preliminary trial at the beginning. But you see that purple color is in the middle, right where it's hitting the solution. That's where the iodine first hits the starch before it can escape and react with the ascorbic acid. But as soon as it gets out of that spot and the ascorbic acid has time to hit it, then it will disappear. Now the advantage of the auto stirrer is that we can speed it up, and that will help that black color to disappear very rapidly, even when you're close to the end point. As you get closer to the end point, that purple color starts to disappear more and more slowly. And rapid stirring, though, it of course causes it to come in contact with more ascorbic acid, and it will still disappear as long as there's ascorbic acid left in the solution to react with it. But it's starting to disappear more slowly as we get close to the end point. I'm almost to 20 milliliters. Actually, I'm at 17 milliliters right about now, and I'm going down to 18 milliliters. It's still disappearing pretty quickly. But I'm going to go ahead and turn this up higher. I'll zoom in even closer here. And if I add 1 drop of iodine, oops, that's not a drop, that was a little stream. There's drop-wise. You see the drops coming out. I can slow it down. That's the advantage of the burettes. You can control that drop extremely precisely when you try. So those drops are going out pretty quickly. I can slow the drops down. Now this would be a very slow drop rate right there. 1, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000. See, that's the joy of titrations, is the slow, patient waiting for the end point. Drop by drop by drop. Oh, there's another drop. Oh, you see that purple color though? It disappeared right away. So we're still not at the end point, obviously. There's a drop, and the purple color disappears right away. In fact, I'm not even past 20 milliliters yet. I can speed it up a little bit. Look at that. That's practically the end point right there. I still see a slight hint of color. So let's go ahead and check that volume. And it's still faded, so one more drop or just a few more drops will probably be the end point. What's the volume at? 20, focused. Oh, there we go. Ooh, there we go. Focus is good. 20.4. Man, that's hard to see still. 20.3. No, it's 20.4. There we go. One drop. Can I do it? Bing! Bing! 2 drops. Ooh, let's go ahead and go for a 3rd drop. Remember, it's gotta stay. The color's gotta stay for 30 seconds or longer. 3, 4 drops. Ooh, I think that's gonna do it. 5 drops. That's definitely the end point. A little bit past it by a drop or so. What's that final volume at? .6. See, man, this is hard to focus. There's 20.5. Looks like the bottom of the meniscus is in between 20.5 and 20.6. So you could say 20.65. Alright, let's record it on our data record here. Initial burette level was 0.00 milliliters. Final burette level is 20.65 milliliters. So milliliters of iodine used, it's just 20.65 minus 0, 20.65. Okay, and we'll calculate milligrams of ascorbic acid in the sample by multiplying this by 0.53. So let's try that out here. Equals 10.9. Technically, we can only keep 2 significant figures on that, but I'll keep 1 to avoid round-up error for now. 10.9. That's milligrams of ascorbic acid. Now I need to do this 2 more times. Now I'm not going to refill the burette until the 3rd trial, so our 2nd trial is going to initially start at 20.65, and then final burette level should be around 41, since it should take about the same amount to do the 2nd titration, because these 2 solutions were mixed, intending them to be identical. So let's put that to the test. What did that one come out to be? Looks like 40, 41, shaky, 41 point. 2. On closer inspection, sorry for the shaky camera, folks, 41.15 is what I got. And so we subtract those two to see how many milliliters of iodine was used. I think that's going to be right on the money, practically the same value. 20.5 for the second titration value. 20.50 if we keep all those significant figures in there, right? And that is definitely a small margin of difference. So we don't practically have to do the third titration because we did so good on the first two titrations. Because this comes out to be 10.9. With insignificant figures, these two are indistinguishable from each other, so when we average those together we get 10.9. And of course, if we go to the correct number of significant figures, we just have 11 milligrams per milliliter. And that is limited by our significant figures primarily by the concentration of the iodine here. We only assume 2 significant figures on the concentration of the iodine, and so if you look at the work on the board, I only wrote 1 significant figure with a 3, but there's 2 that we can claim, and so that allows us to keep 2 significant figures right here. Okay, so now we just need to come down here and look at this question primarily to see how our results compare to the daily recommended allowances and what the label on the bottle claims for the amount of ascorbic acid. So back into the classroom we go. Why is there a chair on top of that table? Who's been horseplaying in this room? No, I got that there to set up my camera so I can record these wonderful videos for you all. Right, back at the board we are. So let's see here. We left off talking about, well, saying I'm going to come back to this 7.7 milligrams. We saw where this 0.53 comes from, and so now I want to use that with our experimental results, or at least show you how to use it with your experimental results to compare to what the label on the bottle says. Okay? So, question number 3 here says the current recommended daily allowance in the U.S. of vitamin C is 90 milligrams per day for a male and 75 milligrams per day for a female. Well, use the above results to calculate how many milligrams of vitamin C are in one serving. That's 240 milliliters of the juice. So that's the typical serving, 240 milliliters. Well, in the lab, we found 11 milligrams of juice. 11 milligrams of ascorbic acid per juice sample. On the board here, I said, well, what if it took 7.7 milligrams of ascorbic acid per milliliter of juice sample, or per juice sample? So the juice sample is 20 milliliters, though. So that's 7.7 milligrams of ascorbic acid. You can write it as per 20 milliliters of juice, right? And so you can set that up as a nice proportion and have it as, to answer this question, you can have it as 7.7 milligrams of ascorbic acid per 20 milliliters of juice. And you say, okay, well, how many milliliters of juice is in the serving for question A? Question A says 240 milliliters. So we could multiply that ratio or proportion by 240 milliliters of juice. And what does that equal? Well, think about this. I mean, it's good to have this stuff make common sense to you whenever possible. You say, I use a 20 milliliter sample of juice, right? Well, how many times more is 240 milliliters for a full serving? Well, 240 divided by 20 is the same thing as 24 divided by 2, which is 12. So 240 is 12 times more juice than we use for our sample. So in fact, all we need to say is 12 times more juice should have 12 times as much ascorbic acid in it, right? And that's what this is showing. Milliliters of juice canceled out here. And we got 240 divided by 20 is 12. 12 times 7.7 milligrams of ascorbic acid says if this was our result, then we would have 12 times 7.7, and you would get 92.4 milligrams of ascorbic acid. And that'd be per milliliter of juice. I'm sorry, well, per serving, because we canceled the milliliters, and this is milliliters of juice per serving right here. So you'd have milliliters canceled and say 92.4 milligrams of ascorbic acid per serving. Okay, that would be the answer if we had gotten in our experiment 15 milliliters for the endpoint, and that would come out to be 7.7 milligrams per. But we didn't get that for our experiment, right? So what you have to do is take the experimental value that we got, which is 11 milligrams of ascorbic acid per 20 milliliters of juice, and do the same calculation right here for part A on question 3, okay? So this would be 3A, and you need to put in, well, the correct number for milligrams that we got from our experiment. Okay, any questions about that, of course, put them in the comments to the video, or email me to, my school email account. And of course, you can do this through Canvas and that kind of thing to get in touch with me with any questions that you have about it. Okay, the next part of the calculation, though, is perhaps more interesting, you could say. I'm going to go ahead and put that up here some and say, well, it says, show whether or not your results support the claim on the label of the fruit punch. Well, if we again found 7.7 milligrams for our experiment per 20 milliliters of juice, does that support the label? Well, it says 92.4 milligrams of ascorbic acid per serving, but the bottle says there's 130% vitamin C per serving. And when it says that on the bottle, it means per bottle. Okay, and the bottle is not 240 milliliters. But it is close enough. It says it's 237 milliliters per bottle, 8 fluid ounces, and again, 130% daily recommended value. So how are we going to say whether or not our results support the claim on the label? Well, if our results from the experiment was this right here, we could use it like this. Say, okay, I got 7.7 milligrams of ascorbic acid per 20 milliliters of juice. I'm going to write that again up here. It says 237 on the label, right? Yeah, we're going to 237 milliliters per bottle, is what I'll put. Then what does that come out to be? Well, we can be picky and say 237 times 7.7 divided by 20. And what do I get? 91.2, which rounds off to 91, which, again, with insignificant figures, 91 and 92, that's the same, okay? Because we only know that last significant figure plus or minus 1, because that's all the precision level that we had. Milligrams of ascorbic acid per bottle. Well, does that support the claim on the label? Not quite. Unless you're a female, it might. You could say, okay, what is 130% of 75 or 130% of 90? Well, all you got to do to figure that out is multiply those numbers times 1.3. Okay, there's a number of different ways looking at percentages and ratios and proportions. I'll just take it like this and say, okay, 130% of 75 milligrams of ascorbic acid for female is going to be times 1.3, and that would come out to be, well, punch it in, 1.3 times 75, 97.5, or 98 milligrams of ascorbic acid per bottle is what the label says from the label. Of course, if it's talking about for an adult male, then it would be 90 milligrams of ascorbic acid times 1.3, and according to the label, it would be 90 times 1.3, 117. So, depending on how you look at it, you can say that this doesn't quite meet the criteria if our results were 15 for the titration for the endpoint. Our results was not. Our results was closer to 20.5, 20.6, higher than this. So that would put this number higher as well from our experimental results, which would come closer to matching one of these values. So maybe we did support the label pretty well. Leave that to you guys to figure out, and let me know of any questions that you have. Good one. Now I gotta clean up this mess.